All right, in this section, we're going to see a bunch of different properties of the trigonometric functions that emerge directly from the definitions. So let's start by recalling the definitions that we worked out in the last section. So the definitions we used depended on an angle and standard position. And recall that an angle in standard position is just an angle with its vertex at the origin, its initial side the positive x-axis, and the terminal side pretty much anywhere. So here we have a terminal side in the first quadrant. And we would let x, y be any point on the terminal side. And that induced this right triangle here, with a length of x, a height of y, and we called the hypotenuse of that triangle r. And we saw that r was the square root of x squared plus y squared. And we defined the 6 trigonometric functions out of ratios of x, y, and r. So sine of theta was y over r. Cosine of theta, x over r. Tangent of theta, y over x. Cosecant of theta, r over y. Secant of theta, r over x. And cotangent of theta was x over y. Okay, very good. So again, what we're doing today is we're going to just play with these definitions and see what interesting properties emerge that will make our lives easier when it comes to working with these functions. And the first thing that we're going to notice here is something that I mentioned in an earlier lecture, which is that these trigonometric functions here are just defined to be the reciprocals of these trigonometric functions here. So while sine of theta is y over r, cosecant of theta is r over y. And that gives us a family of identities called the reciprocal identities. So we could say that sine of theta is 1 over cosecant of theta. And cosine of theta is 1 over secant of theta. And tangent of theta is 1 over cotangent of theta. We could also see that cosecant of theta is 1 over sine of theta. Secant of theta is 1 over cosine of theta. And cotangent of theta is 1 over tangent of theta. So what this tells us is you only ever need to know sine, cosine, and tangent, and if you know those three, then you know the other three for free, just by taking the reciprocal of whatever function. So let's suppose we were given cotangent of theta. We're told that it's equal to 4, and we want to determine tangent of theta. Well, indeed, tangent of theta is 1 over cotangent of theta, and we know what cotangent of theta is, so we can replace cotangent of theta with 4. All right, and now we want to find cosine of theta, given that secant of theta is negative root 5 over 2. Well, let's throw another indeed in there. Indeed, cosine of theta is 1 over secant of theta. So that would be, you can write it as 1 over negative rad 5 over 2, but it's probably easier just to take the reciprocal directly and say, well, this is negative 2 over rad 5. Let's rationalize that denominator. So we get negative 2 rad 5 over 5. All right, let's take a closer look at x, y, and r. Notice the way r is defined, that r is always positive. Okay, r can never be negative. In fact, it's this length along the terminal side where the dot is. So that's always positive. However, x and y could each be positive or negative. Now, in this particular drawing, x and y are both positive, and that's because we're in the first quadrant. However, if our angle were a second quadrant angle, this would still be y, and this would still be x, and there would be r. You can see now that x is negative, right? A second quadrant angle would involve a negative x value and a positive y value. And using that information, we can make a prediction about which trigonometric functions will produce a positive ratio and which ones will produce a negative ratio. For instance, in this situation, sine of theta, which is y over r, is made up of a positive number divided by a positive number, so sine of theta will be positive. However, cosine of theta, which is made up of x over r, would be a negative number divided by a positive number, and would therefore be negative. So whether a trigonometric function produces a positive or negative ratio depends on the quadrant of the specific angle being evaluated. So what we'd like to do here is see exactly which functions are positive and negative in each quadrant. All right, let's take a look at the quadrants here. So we have quadrant 1, 2, 3, and 4. Now on the right half plane, we know that x is positive, and on the left half plane, we know that x is negative. In the upper half plane, we know that y is positive, and in the lower half plane, we know that y is negative. So each quadrant involves some combination of x and y being positive or negative. Knowing that r is always positive, and knowing how each trig function combines x, y, or r, we can predict exactly which ones will produce a positive ratio and which ones will produce a negative ratio. So in the first quadrant, x is positive and y is positive, and of course r is always positive, so everything's positive, which means that all the trig functions will be positive. In the second quadrant, we have that x is negative and y is positive. So only the trig functions whose definition involves y are going to be positive, and that would be sine and cosecant. With the rest of them being negative. And in fact, for the other quadrants, there will only at any given time be 2 positive trig functions, with the rest being negative. So we're only going to write down the positive ones. In quadrant 3, both x and y are negative, which means pairing either of those with r would produce a negative ratio. However, pairing them with each other would produce a positive ratio, as a negative divided by a negative is positive. So the trig functions that involve exclusively x and y will be positive. That would be tangent and cotangent. Okay, and finally, in the fourth quadrant, we have x is positive and y is negative. So since x is positive and r is positive, any trig function involving x and r is going to be positive. And that would, of course, be cosine and secant. So in the first quadrant, they're all positive, but in the other 3 quadrants, only 2 of the trig functions are positive, depending on the quadrant, with the rest always being negative. So there are some helpful mnemonics here. You can make up your own, but I'll share a couple with you here. A, S, T, C. Okay, read in this order. First quadrant, second quadrant, third quadrant, fourth quadrant. So A, S, T, C, where A stands for all, S is sine, T is tangent, and C is cosine. And the mnemonic that's commonly used is all students take calculus to remember this. All students take calculus. Okay, that's not a true statement, of course, but it's good for memorizing this. Also, all soup turns cold. ASTC. All right, so that only acknowledges the principal three trig functions, doesn't acknowledge the cosecant, cotangent, or secant, but if you understand the reciprocal identities, then you only need to know what happens to sine, tangent, and cosine. Okay, let's look at some trigonometric expressions and see if we can determine their sign, whether they're positive or negative. So we'll start with tangent of 1,340. So the first thing we're going to need to do is determine the quadrant of that angle. Well, it's not clear. The only obvious ones are angles between 0 and 360. So in order to do that, we should find the angle coterminal to 1340 that's between 0 and 360. Okay, well that process involves, in this case, subtracting 360 degrees a bunch of times. But let's just subtract 1080 all at once, because we know that that's 3/360s, and we know that's going to be enough to work. So if we subtract 1080, that's going to give us 60 plus 200, so that's 260 degrees. Okay, well we certainly need to know the quadrantal angles that separate all the quadrants. So there's like 0, 90, 180, 270, and 360. So when we have an angle of 260 degrees, well, we know that that must be somewhere here in the third quadrant. It's a little bit less than 270. In fact, it's even more extreme than I've drawn it. It's a lot closer to that 270. But it doesn't matter. The fact that it's in the third quadrant is all we care about. So we can see 260 degrees is in quadrant 3. And now to determine whether tangent of 260 degrees is positive or negative, we'll use this mnemonic here. All students take calculus. And in the third quadrant, we can see t for tangent is positive. So in fact, tangent of 260 is positive. And we actually can conclude that tangent of 1340 is positive, or greater than 0, which means positive. Okay, let's go with sine of 295 degrees. So is that positive or negative? Now 295 is between 0 and 360, so this one will be a little easier than the last one. 295 is somewhere in the fourth quadrant. It's between 270 and 360, in fact. All students take calculus. In the fourth quadrant, we can see that cosine and secant are positive, but we're taking the sine of 295, so that must be negative then. Sine of 295 degrees is negative. Okay, secant of negative 60 degrees. So let's locate negative 60 degrees. Negative angles are read clockwise. So again, we can see fourth quadrant. And fourth quadrant, we know ASTC, right? So cosine is positive, but secant is the reciprocal of cosine. So whatever cosine's doing in terms of plus or minus, secant will follow suit. So we in fact know that the secant of a fourth quadrant angle is positive. Okay. Cotangent of 51 degrees. 51 degrees is between 0 and 90 degrees. It's about like there. So it's an acute angle. And we can see that it's certainly in the first quadrant. 51 degrees is in quadrant 1. And all trig functions are positive in the first quadrant. That's the A. All students take calculus. All soup turns cold. right? So no matter what, cotangent of 51 is positive. So cotangent 51 degrees is positive. All right, let's do one more. Tangent squared of 120 degrees. So remember, what does it mean to have this little 2 here? It means we're actually squaring the tangent of 100 degrees. So it basically means work out the tangent of 120 degrees, whatever that is, and then square your answer. Okay. Well, this is good news for this particular question, since all we're asking for is whether the answer is positive or negative. So whether or not tangent of 120 degrees is positive or negative, when we square it, it will become positive. So we actually can just say right away this is positive. However, I think it's a good exercise to quickly just locate 120 degrees in standard position. It's about here. So we can see that tangent of 120 degrees is in quadrant 2. And according to all students take calculus, the S is in quadrant 2 there. So that would mean that sine and its reciprocal cosecant are the only positive functions. So tangent of 120 degrees is negative. However, when squared, the result will be positive. So we can conclude that tangent squared of 120 degrees is positive. Okay, we can also use our knowledge of quadrants to pinpoint the specific quadrant of theta given some information about it. For instance, we have some angle in standard position, and we're told that its tangent value is positive and its cosecant value is negative. So what's the quadrant of theta? Well, we'll have to do a little investigating here. Let's quickly write down our mnemonic here. All students take calculus. And we can see that since we're given that tangent of theta is positive, theta is in quadrant 1 or quadrant 3, because those are the quadrants we know tangent is positive. Of course, quadrant 1, everything's positive, and in quadrant 3, tangent and cotangent are the only positive functions. So that rules out quadrant 2 and 4. Now, since cosecant of theta is negative, theta is in, well, where's cosecant positive? So all the functions are positive in the first quadrant, so this rules out the first quadrant. In the second quadrant, sine is positive, and therefore cosecant is positive, so that rules out the second quadrant. In the third and the fourth quadrant, sine is negative, and therefore cosecant is negative, so theta is in quadrant 3 or quadrant 4. But combining this information tells us that theta must be in quadrant 3. So the range of sine theta and cosine theta, meaning the set of possible outputs, are just numbers between -1 and +1. Okay, so for instance on a calculator, if we go sine of, it doesn't matter what number you put in here, 1, 2, 3, 4, 5, that's my luggage combination, the result will always be something between -1 and +1. In other words, this is 0 point something. You're never going to get 1 point something or 17 point something. Okay, however, tangent and cotangent, consisting of x and y, can be any ratio. So their ranges are -infinity to +infinity. So you could get any number out of tangent or cotangent. Let's go tangent of 1, 2, 3, 4, 5. And here we get -3.7. Well, that leaves cosecant and secant, but those are the reciprocals of sine and cosine. So if you take a number that's between -1 and 1, and you take its reciprocal, you're actually going to get a number that's specifically outside that range. So you'll get everything but those numbers. So that's -infinity to -1, union with 1 to infinity. In other words, cosecant and secant of any angle will never result in 0 point something. It will always result in 1 point something, or 2 point something, or 5 point something, possibly negative. So we can use this fact to determine whether or not a statement is possible. So if somebody came along and said, I'm thinking of an angle whose cotangent is -1/2, is that statement possible? And for this situation, yes. Tangent and cotangent can output anything. They have no restriction on their output. So cotangent of an angle equals whatever number you want, that's possible. All right, now somebody comes along and says, I'm thinking of an angle whose cosine value is the square root of 2. Well, that's impossible. The square root of 2 is about 1.4. And 1.4 is outside the range of -1 to 1. So there is no such angle, not in the real numbers. And what about somebody coming along and saying, I'm thinking of an angle whose cosecant value is 0? Well, that's also impossible, because 0 is between -1 and 1, so it's not in the range of cosecant and secant. The range of cosecant and secant is everything outside -1 and 1. Okay, for the rest of this section, we're going to uncover a few more fundamental identities that are very helpful. First, we'll discover the quotient identities, followed by the Pythagorean identities. So let's take a look at the quotient identities. We know that tangent is defined to be y over x. Okay, so just for fun, we can divide the numerator and the denominator by r. And what that would give us is, in the numerator, y over r, which we know is the definition of sine of theta. And x over r, we know is the definition of cosine of theta. So we have this beautiful little fact that we can conclude, which is that tangent of theta is sine of theta divided by cosine of theta. Okay, and since cotangent of theta is the reciprocal of tangent of theta, we can conclude that cotangent of theta is cosine of theta divided by sine of theta. And this gives us the quotient identities. Tangent of theta is sine of theta divided by cosine of theta, and cotangent of theta is cosine of theta divided by sine of theta, which means if you know both sine of theta and cosine of theta for a specific angle, you can calculate tangent of theta just by taking sine of theta divided by cosine of theta. Note that identities are classically written in a certain way, and this is the way that these quotient identities typically appear. But you should be aware that when you're working with them, you might encounter something like tangent of theta times cosine of theta, and just be aware that that's equal to sine of theta. That's just this quotient identity with both sides multiplied by cosine of theta. So they do appear in various forms depending on the context that you're using them. Okay, once again, let's take a quick look at an angle in standard position here. Now we can see, as we've noted in the past, that by the Pythagorean theorem, x squared plus y squared is equal to r squared, because we have a right triangle. So if we took that x squared plus y squared equals r squared. And just for fun, if we divided every term by r squared, so here's our x squared plus y squared equals r squared, and now we're just dividing everything by r squared because that's fun. Then this term becomes x over r quantity squared, and here we get y over r quantity squared, and here we get r over r quantity squared. But knowing our definitions, we can see that this is cosine as a quantity squared. We'll write that as cosine squared of theta, plus y over r, which is sine of theta, again as a quantity being squared, is equal to r over r, that's 1, and 1 squared is 1. So we arrive at this, which is a fundamental identity. It's called a Pythagorean identity. And we'll come back to that one in just a moment, but let's actually go a step further here, and let's divide both sides of that by cosine squared of theta. So what we have is, well, here's where we started. And now we're dividing everything by cosine squared. So, okay, cosine squared over cosine squared is 1. Sine squared over cosine squared, well, this is like sine of theta over cosine of theta, all being squared. And this is like 1 over cosine of theta, which is all being squared. So sine over cosine, we know that's tangent, so this is tangent squared. 1 over cosine is secant, so this is secant squared. And we get another Pythagorean identity. But it doesn't stop there. Now let's go back to the first Pythagorean identity we found, which is kind of the main one, cosine squared plus sine squared equals 1, and divide both sides by sine squared. Last time was cosine squared, this time is sine squared. So what we have is cosine squared theta plus sine squared theta equals 1, and we're dividing each term by sine squared theta. So here we get cosine over sine, and that quantity is being squared. Sine squared over sine squared is 1. And here we get 1 over sine of theta, which is being squared. Cosine theta over sine theta, we know is cotangent, so that's cotangent squared, plus 1 is equal to cosecant squared theta. And that gives us one more identity. So these three that we've just found are called the Pythagorean identities. So they are cosine squared plus sine squared is equal to 1. And 1 plus tangent squared is equal to secant squared. And the last one we found, which I'm going to rearrange the terms just so that it's structurally similar to the one above it, is 1 plus cotangent squared is cosecant squared. And these last two have helpful mnemonics. This one here, think of the sentence I tan secretly. And for the other one, think of the sentence 1 coat in the closet. So those mnemonics are only helpful if you understand the structure of the identity that you're expecting. But if you do, then they are very helpful mnemonics. Okay, well, something remarkable about trigonometry is that it forms its own sort of little mathematical ecosystem. And what I mean by that is, if you know one tiny little thing like that we know that cotangent of theta is negative 5 over 7, and we know roughly where theta is located, which is between 0 and 180 degrees, so it's in the upper half plane, then we're going to be able to deduce the values of all 6 trigonometric functions. Well, we have 1 already, so there's only 5 left to get. And we're going to use identities to do this. And we're just going to use the identities that we've already figured out. So first of all, let's make a little area for our final answer so we can keep track of what we know and what we don't. So sine, cosine, tangent, cosecant, secant, and cotangent are what we have to figure out, and we already know cotangent is negative 5 over 7, so look, we're a sixth of the way through solving this problem already. So what we want to do is appeal to the identities that we know to figure out the rest of these function values. Now, tangent's really easy to get because it's just the reciprocal of cotangent. So let's find that one first. So indeed, tangent of theta is 1 over cotangent of theta. So it's going to be just negative 7 over 5, the reciprocal. Very good. So now we just have to figure out the other ones. Now, a really common error here that you definitely should not make is to say, oh, well, we have tangent. It's negative 7 over 5. And we know that tangent is sine over cosine, which must mean that sine is negative 7 and cosine is 5. And that is definitely not true. It just means that the actual value of sine divided by the actual value of cosine would give us negative 7/5. It does not mean that sine is literally the numerator and cosine is literally the denominator. In fact, we know that sine and cosine have to be between negative 1 and positive 1, so they can't ever equal 7 or 5. Right? So how exactly would we proceed at this point? Well, we can use a Pythagorean identity. If you look at the Pythagorean identities, you may notice that each trigonometric function among the 6 appears exactly once, which means there'll always be a Pythagorean identity that involves whatever the given function in the problem was. In this case, we were given cotangent. So let's use that Pythagorean identity there, 1 cot in the closet, and we'll use that to find cosecant. 1 cot in the closet. All right, so cosecant squared of theta is equal to 1 plus cotangent squared of theta. So that's the square of cotangent of theta. Well, cotangent of theta was given as negative 5 over 7. So when we square negative 5 over 7, we get positive 25 over 49. And with a common denominator here, we get 49 plus 25, which is 74 over 49. So cosecant squared is 74 over 49. That means that to find cosecant, we would just take the square root. However, if our answer ought to be positive or negative. So we need to actually figure out whether our solution here is positive or negative. And the answer to that depends on the quadrant of theta. So what were we given? We were given that cotangent of theta is negative 5 over 7. And we were also given that theta is between 0 and 180 degrees. So the 0 to 180, that tells us that theta's in quadrant 1 or 2. Cotangent of theta is negative. That rules out quadrant 1. So now we know that theta is in quadrant 2. So now, if we go back to cosecant of theta, we can establish whether or not this is positive or negative. And if you think about all students take calculus, we are in the second quadrant, so we know sine is positive and cosecant is positive. So our answer here for cosecant will be positive rad 74 over 49. And distributing the radical, we have rad 74 over the square root of 49, which is 7. So there's our cosecant of theta. So we'll write that in as our final answer here. Cosecant of theta is rad 74 over 7. We can also now take advantage of a reciprocal identity, because if we know cosecant, we certainly know what sine of theta is. It's just the reciprocal. So the reciprocal of cosecant would be 7 over rad 74. Let us rationalize that denominator, and we get 7 rad 74 divided by 74. And let's go put that in as our final answer. Sine of theta we now know is 7 rad 74 over 74. So that just leaves cosecant and secant to figure out. Of course, once we know one of them, we will get the other one, again by just taking its reciprocal. So, okay, well, how can we find one of those? Well, certainly you could use a Pythagorean identity, like knowing that cosine squared plus sine squared equals 1. You could solve that identity for cosine, and you're good to go. You could also use I tan secretly to relate tangent and secant, and we would determine secant that way, and again, we're off and running. However, since we have 2/3 of a quotient identity, I think we should use tangent is sine over cosine. So we know that tangent of theta is sine of theta over cosine of theta, and we're interested in cosine of theta, so we'll multiply both sides by cosine of theta, and we get cosine of theta times tangent of theta is equal to sine of theta. And now we'll divide both sides by tangent of theta. And so we get that cosine of theta, which is what we're after, is sine of theta divided by tangent of theta. And we have both of those ingredients. In fact, sine of theta was 7 rad 74 over 74, and tangent of theta was negative 7 over 5. So we just have to clean that up. Let's write it as multiplying by the reciprocal. And we can cancel the 7s. So for cosine of theta, we get negative 5 rad 74 over 74. And let's quickly find secant of theta, which we know is just the reciprocal of that. Secant of theta is 1 over cosine theta. So that would be 74 divided by negative 5 rad 74. It's the reciprocal of cosine. And rationalizing that, we would see that the 74 in the numerator cancels with rad 74 times rad 74, which is 74. And so we get negative rad 74 over 5. And we can place those in our final answer. And there we are. We purely used identities to deduce all of the remaining 5 trigonometric functions when we were given simply cotangent and some vague information about the location of the angle theta. Notice that as theta was indeed established to be a second quadrant angle, that everything is negative except for sine and cosecant, which are both positive. Now, final comment here. You may already know how to solve a problem like this purely by drawing a triangle and appealing to what's called SOHCAHTOA. Okay, you may have seen that from high school. You have my blessing to solve this problem that way. It's certainly more compact. It doesn't involve quite as much writing. We will cover that technique in Chapter 2 very soon. So if you do want to use that, go ahead. I'm not here to restrict you. But you do need to overall understand these identities, because there will be more complex versions of this problem in Chapter 5 where triangles are not going to help. You just have to use identities.